All right, we're on page 129 of the note spiral. And please have it open up so that you can also see your recipe for success for hypothesis testing. Really important that you keep up with that step-by-step procedure on how to work the problems, because we will follow that exactly. So I'm going to work this a little bit differently than I did in class, because I'm going to show a little bit more information than we talked about in class. So the EPA reports that the exhaust emissions for a certain car model has a normal distribution. So they're telling me the underlying distribution is normal, with a mean of 1.45 grams of nitrous oxide per mile. So they're saying, hey, the claim is, or the status quo is, it's 1.45 grams of nitrous oxide. The car manufacturer claims their new process reduces the mean level of car exhaust for this model. A simple random sample of 28 cars, so we have n equals to 28, is taken. The mean level of exhaust emitted for this sample is 1.27, so they're telling me my X bar, my sample is 1.27, and the standard deviation of the sample is 0.4, so S of X is 0.4. Is there statistical evidence at an alpha level of 0.05 to support the car manufacturer's claim? So they're also saying they want me to run this test at 0.05. All right, so let's go back and let's work on writing our null and alternative, and then we're going to do a little bit of a side note, and then we'll work the entire problem. So first off, we need to write our null hypothesis, which we always express as HO. So we're expressing it as HO, and what is the status quo? What has been the general claim? What have we said before? What has been going on? And that's always a null. We always express it as the Greek letter. So in this case, mu. I don't draw a very good mu, so it looks like an M, but mu equals 1.45. All right, specifically it's 1.45 grams. It really helps to have a label. The alternative, well, they said reduces, so I'm going to say this is going to be a less than. So mu is less than 1.45 grams. Now this is a major caution. Make sure you're using mu. You're always going to use the population parameter symbols here. If you use an X bar here, you're losing 25% of your score. All right, so just don't do that. Make sure you're using the population parameter symbols. All right, and while we're here, we're going to go ahead and define what mu is. And we're going to say, let mu equal the true population mean grams of nitrous oxide. All right, so let mu equal the true population mean grams of nitrous oxide. Normally at this point I'd go ahead and I'd start working on my conditions, but I'm going to set that aside for just a moment. All right, they told me the underlying distribution was normal, and so that means I'm going to have a bell-shaped curve. And because we have a standard deviation of the sample, we know we need to be working with a t statistic. So this lets me know that I have to work with a t. And I know one of the questions is hey, well, I don't understand this alpha, this p-value, and this critical value business. So hopefully this will help. Well, we know that we're working with a less than because that's what our alternative is. We know that our sample is size 28. I know our degrees of freedom are 27. So I'm going to go ahead, alpha being the area in the tail, I'm going to go ahead and run this real quickly and get a t statistic, second vars, inverse t, and I end up getting 0.05. And that gives me a critical value of negative 1.0732. And what that tells me is this right here, because all t statistics are centered around 0, anything that is, if I get a test statistic after I run everything, after I use t equals x bar minus mu s divided by the square root of n, when I run that, if I get a t value less than negative 1.703, I'd be rejecting. Now, we always express in p-values. And so if I get a probability, if this probability is less than 0.05, I also reject. If I get a value to the right of 1.7, I fail to reject. If my p-value is greater than 0.05, I fail to reject. So hopefully that will help when we actually come back to running this test, so that you'll have a good understanding of critical values in alpha. So our conditions are as follows. The first one, we need a random sample. And they told us that it was a simple random sample. So that means it was given. All right, so we're good there. The next thing, we need to have our sample needs to be less than 10% of the population. So 28 divided by 0.10 equals 280. All right, I really don't know this, but I have to assume that there are at least 280 cars of this model. At least 280 cars of this model. Therefore, the sample is less than 10% of the population. Once again, this is back to that giant pile of M&Ms. And it says that we're doing it without replacement. So technically the percentages are changing, but it's changing so slightly we don't worry about it. So really we're saying they're independent enough. They're not really independent. They're independent enough. Don't ever write this on the test. Don't write this on the AP exam, but occasionally that'll show up as like a multiple choice type test question. Number 3. We need to check normality. And there's 3 ways to check it. We can check the data to make sure that the graph is normal. We can check it by central limit theorem. Well, in this case, our sample is too small. It's not 30 or more. But fortunately, they told us it was normal. And so we can say the population is normal. And why can we say that? They told us so. So in other words, it's a given. So we're good there. So we don't have to do anything more with that. All right. So now that we've done that, the next thing says write the equation. Well, the equation we're going to be working with is the basic t equation, which is t equals x bar minus mu s divided by the square root of n. All right. And it says draw the graph. Well, the graph associated with this in this particular problem is simply this. We have a mean claim of 1.45. This is going to negative infinity. This is going to positive infinity. And we have a sample mean of 1.27. X bar right here, 1.27. And what we want to know is how likely it is that I would get a sample mean of 1.27. How likely is it I'd get a value that extreme or less if 1.45 was the actual value? And so that's what we're going to check. So we're going to start plugging in. And so because we're going to want the probability that X bar is less than 1.27, which is going to be the probability that T is less than 1.27 minus 1.45 over 0.4 divided by the root of 28. So on the calculator, stat test, t-test, and I have mean of 1.45, x-bar 1.27, standard deviation 0.4, 28. Now, be really careful. This says less than, this says less than, this says less than. So make sure that we have facing our inequality in the same direction when we press calculate. And so we end up getting the probability that t is less than negative 2.3811 equals 0.0122. All right. This part right here, that's our p-value. This is our test statistic. TS for test statistic. All right. So we need to compare our p-value to alpha. And so I just always do this. I write p-value. I write alpha. Our p-value is 0.0122. Our alpha was 0.05. And because it's in the middle of a test and you're under stress, make these the same length. So this is 4 digits, so I need to add 2 zeros. And real quickly, I see that 500 is bigger than 122. So my decision is to reject HO. That's my decision. We're going to reject the null. All right. So we've now labeled this out really nicely and straightforward, and we need to go write our conclusion. All right. Please do not change the conclusion. Please do what it says. All right. Follow that template. So our p value is 0.0122. We reject the null. All right, we just said that we no longer believe the initial claim. We no longer believe the null hypothesis. There is sufficient evidence at alpha equal 0.05. And if you want to write the word alpha out, that's fine. That you can do. To suggest, we're going to restate our definition that we wrote earlier to suggest that our definition was the true population mean grams of nitrous oxide is less, by the way, is less, that's what that says, is less than 1.45 grams. All I did right here is write the alternative hypothesis in words. So our p-value is 0.0122. Our decision was to reject the null because our p-value was less than alpha. There's enough evidence, and I like to use the word sufficient evidence at what was our alpha, 0.05, to suggest the true population mean grams of nitrous oxide is less than 1. All right. Now I want to go back to what we did at the very beginning. At the very beginning, we did a second bar as inverse t, and we got a critical value of 1.7032. Well, our test statistic is negative 1.2381. So our test statistic is somewhere out here. So because it's further to the left, and we said anything further to the left we were going to reject. We could have rejected because our test statistic was less than our critical value of negative 1.7032. Our test statistic of 2.3811 was less than this. We also said that our p-value of 0.01 was less than 0.05. Therefore, we also reject. One last thing. They won't always tell you the alpha level. They won't always give you the level of significance. If they do not give that to you, please use 0.05. So if they do not give you the level of significance, please use 0.05. Also, I'm just going to stress it again. This conclusion is very well thought out, and our p-value is whatever we calculated. Our decision was to reject a null. If it had been failed to reject, we'd go to the one below it. There is sufficient evidence at alpha equals whatever the alpha level was to suggest the true population, restate the definition of the parameter, and then restate the alternative. And our alternative was less than 1.45. You're restating it in words, okay? All right, so that's our first video. We will do another one in just a moment, and I think we're failing to reject in this